When a clockmaker is building a clock, they want it to run at a constant rate. That is to say, when the clock says 1 second has passed, 1 second has actually passed. The rate is essentially distance per time, distance the hands move per time. The per indicates that you've got a rate, you've got a derivative. Now, measuring the rate directly involves measuring how fast the gears are turning, how fast the pendulum is moving, and that starts and stops. That's what you hear when the clock ticks. So what really gets displayed on the hands is the integral, or the antiderivative of that rate. The rate's a little hard to measure directly. So what a clockmaker does when they want to measure the rate, because that's how you tell if it's a good clock, is that its rate is stable and correct. What you need to do is you need to take the derivative of that antiderivative of the rate. You get back the rate then. That's the second part of the fundamental theorem of calculus. Now you might ask, okay, I'm telling how many seconds the clock said have passed versus how many seconds actually passed. How do you know that? How do you measure the amount of time that's actually passed? Well, nowadays we use GPS, but in the past, clockmakers would actually use the motion of the stars. So by looking at the stars, they could tell how fast the Earth is turning and use that as a reference.
So the second part of the fundamental theorem of calculus is essentially the opposite statement to the first part. So this statement says that if I take the derivative of an integral, I get back the original function. But rather, it's derivative of an antiderivative, really. The integral is constructed in a particular way. So the statement here says that if f is a piecewise continuous function on some interval, that if I take the derivative of the antiderivative, or the derivative of the integral from a to x is in that interval, of f of t dt, I get back f of x. So thing to notice is that where I'm evaluating the function is at the upper limit of my integral. This a does not seem to matter, except to ensure that the integral exists, is well defined. That's really what the role of the a is, because x has to be between a and b. If you go outside of that a and b with x, anything can happen. Okay, so how do I prove this? Well, in order to do this, I need to sort of delve into antiderivatives a little bit. And antiderivatives are kind of the opposite of derivatives. So how do they work? Well, they work like this. So let me say an antiderivative. An antiderivative of a function f is another function, capital F, for which f prime of x is equal to x for all x under discussion. And if I write out the part 1 fundamental theorem of calculus for f prime, you'll notice that something like this works, and just a little substitution, we get a statement like this. So this is the first part 1 of the fundamental theorem of calculus says that. Just rewritten a little bit. Now, one thing that you can notice right away is that I could rewrite my antiderivative. So notice every antiderivative is of the form integral from a to x f of x dx. Well, so I've got too many x's, don't I? So let me avoid any confusion and say f of t dt plus some constant. Some constant I don't know. Okay, so this antiderivative is always of this kind of form. Now, when does this exist? This exists when f is piecewise continuous, based on the definition of the Riemann sum. So this exists provided little f is piecewise continuous. Okay, with these pieces in mind, it's now enough to go back to our original statement and prove this theorem. It's just a little calculation involving the definition of the derivative. So let's do it. And just so you don't think I have any tricks up my sleeve, I'll just copy this here down below. Okay, so proof. So I'm going to rewrite this. This is a derivative. So I'm going to say this is the limit as h goes to 0 of 1 over h integral a to x plus h f of t dt minus integral a to x f of t dt. That's just the definition of the derivative. Now, since I know what this is, I know this expression describes an antiderivative. Let's suppose f of x defined by this expression. Notice by fundamental theorem of calculus part 1, this f is an antiderivative. Okay, so given that, let's continue our calculation a little bit. So let's continue this calculation. So what am I going to do? Well, I'm going to evaluate these two integrals. This one is f of x plus h minus f of a minus f of x minus f of a. And a little bit of simplification here. You should notice right away that the f of a is cancel. And we're left with this expression, and what do you know? This is f, capital F prime. And since we knew that was a derivative, an antiderivative, it gives us f of x. So just as we wanted. And that's the end of the proof. So this establishes the second part of the fundamental theorem of calculus.